Hello, everybody. So we will discuss hadronic physics. There will be another lecture on Wednesday. So this is a kind of introduction. We will go in more details on Wednesday. So we will go through the hadronic models, cross-section, and framework in Gen 4. Then I will say a few words regarding physics list. There will be a dedicated lecture on physics list on Friday, last day. So we will touch very briefly and concentrating on the hadronic aspect of physics list. And then I will say a few words regarding validation. And then I will conclude suggesting some exercise for you if you want to learn more about hadronic physics and not only hadronics. Okay, so first of all, hadronic physics stands for hadrons. So hadrons are particles like pions, proton, neutron. There are 100 different hadrons. And basically, they are all made of quarks, and they all go through the strong interaction. So in many applications, certainly in high energy physics, but not only in space, for instance, cosmic rays or medical physics, if you have to do with hadron beams, you basically have these hadrons traversing some detector made of different type of material. So if we want to make a simulation, we should be able to model the strong or hadronic interaction of any of those hadrons with the nuclei of any material, essentially. So we have to model this hadronic strong interaction. In principle, it doesn't look a particularly difficult effort because we know very well since 50 years the underlying theory, which is QCD, quantum chromodynamics, which is a quantum field theory part of the standard model. So it's known very well. Unfortunately, it is known, so we know the equation, but solving it is another business. It's still, after 50 years, still very difficult. Basically, we are able to do so-called perturbative calculation in a very narrow, extremely important, a very narrow phase space, which is essentially very high energy collision with high energy transverse momentum, which is important because all the interesting physics, for instance, of the EP experiment, W, Z, X, eventual supersymmetric particles, and so on, they are produced exactly in that very narrow phase space. But of course, for the sake of detector simulation, we need to model the whole phase space, not only this narrow, although important part. And basically, as for today, we need to use hadronic models, not the QCD theory, but models, which are really approximations, sometimes very rough approximation. And so for each basically combination of particle type, energy, and target material, we have to have at least one model which tell us what is happening in the case of an interaction, basically. And we need several of them. So this is just we will not go through all the details, but the message here is an example of the models inside Gen 4. And on the x-axis is the energy, the kinetic energy in the lab frame of hadrons. You can think about a pion, a proton. The y-axis doesn't have any meaning, it's just showing the different models. And you see that the most important thing is that models are applicable to some energy range. So there is not a single hadronic model which covers everything. So you need to make a patch of different models to cover all the possible energies. So just to give you a bit of a flavor, this is what's happening at different energy when there is an hadronic interaction, roughly speaking. So for instance, if we start on the top left, the string, the hadronic string model, so at high energy above a few GeV, up to TeV, and what is happening is that the interaction is described in terms of the constituent quarks, and the concept of strings derive from the kind of strong flux that has been also confirmed in lattice QCD and so on. So this is the model which has a little bit of justification from QCD, but is really far, is much simpler than QCD. At lower energy, let's say from 100 MeV up to 5, 6 GeV, there are so-called intra-nuclear cascade models. And here the interaction is described between the hadron as a whole, without looking at the constituent quarks, with the nucleons of the target nucleus. That means proton and neutrons. And inside, there is a kind of mini cascade, a mini transportation, if you want, inside this target nucleus. The part below, a lower energy, we are here in the realm of nuclear physics. So there are two steps. The first one happening at higher energy with respect to the last one, let's say below 100 MeV down to roughly 10 MeV, is called pre-equilibrium or pre-compound. Basically, you have the leftover after the interaction from the hadronic string model or the intranuclear cascade, where you have a highly excited fragment. And there, the description is in terms of holes and excitons. And this is a system which is not only excited, but is even far from a kind of thermodynamical equilibrium. And this system goes in a statistical thermodynamical equilibrium, but still excited, which is the last step, through the emission of light fragments like deuteron, tritium, or proton, neutron, and gammas. The last step on the bottom right is when we have this excited nucleus, so in a statistical equilibrium, but not in the ground state, and it will go through to the ground state by emission of lower energy gammas, proton, neutron, and light fragments. So these are essentially the four main building blocks that we need to describe hadronic interaction. A very important concept, and also sometimes leading to some misunderstanding from the user, is that in Geom4 there is a clear separation between hadronic cross-sections, which describe the probability of having an hadronic interaction, with the final state. So what happened once that we know that there is an hadronic interaction? What is the result of that hadronic interaction? How many particles are produced, which type and which direction, which energy, essentially. This is so we have a separation. So the same cross-section can be used by different final state models. For each combination of projectile, energy, and target, think 10 GeV proton on a copper nucleus, for instance, we have to have at least one cross-section able to cover that triplet, projectile, energy, and target, and at least one, maximum two final state models. If there is one, of course, we use that one. If there is none, it will crash the program because it's not able to produce a final state, doesn't know what to do. If there are two, only in a certain case, I will come back in a second, then we throw a random number and we decide which of the two models to pick. And I will explain you how it works and why we are doing that. The reason is essentially we are assuming some simple linear transition between these two models, and the reason is to avoid some unphysical kinks, unphysical distributions that are due to the fact that these two hadronic models, typically they are coming from different approximation, different things, and if you have a sharp transition, you will see some kick in the observables. So in this way, we do a smearing, and we will avoid to see unphysical things. So let's look at the upper part. This is for cross-section. So in general, we could have as many cross-section as we want. And the idea is that we pick the last one that we put. The idea is that the last one will be the most precise for that particular case of particle type, energy, and target nucleus. For the final state on the bottom, the situation is different. So this is the energy, imagine the energy of a hadron, or a proton, for instance. If we have a physics list like this, whenever we will come here at the runtime, it will crash because there are no final state here, you see. But also, this is a choice of Geom4. We don't accept a situation like this in which there are full overlapping between two hadronic models. What is possible instead is something like that. So you see, If you are here in this energy, we use only model 1, is the only one. If we are here, we are using only model 3 because it's the only one. And here is the transition region where this is allowed, it's fine. This is called transition region. And here we throw a random number for each interaction. We decide which of the two models we use for that thing. I will come back to that in this picture, which is more clear. So these are two physics lists, different. We will cover later. And you see on the x-axis is the kinetic energy in the lab frame in GeV of a proton, a pion, for instance. And the y-axis means the probability of picking that particular model. So you see here, below 3 GeV, we are using Bertini. There's only Bertini. We are using 100% this hadronic model. Above 6 GeV, there is only this FTF, which stands for Fritjof string model, plus P, which is pre-compound excitation, and we use only that. Between 3 and 6, we have this transition region, and we assume a linear probability. That means that we are in the middle at 4.5 GeV. We throw a random number. If it's less than 0.5, we use Bertini. If it's above, we are using FTF. If we are getting close to 3, we draw a random number, and more likely we are using Bertini, then, and vice versa. When we are getting closer to 6, we are using more frequently FTFP than Bertini. Again, the reason is to avoid physical kink in the observables. Here in QGSP Bertini, another physics list, the situation is similar, but there is another transition happening at higher energy because there is a transition between 12 and 25 GeV between the two-string model, QGS, which stands for quark-gluon string model, and the Fritjof string model. Regarding the cross-section, so there are two hadronic cross-sections in general for hadrons, which is the elastic cross-section and the inelastic cross-section. So elastic cross-section means when a hadron interacts with a target nucleus, and in the final state, you find exactly the same two particles, the same target nucleus and the same projectile, and the target nucleus is in the ground state. So the only thing which is happening is that there is some exchange of momentum, some deviation between, some angle between the two. All the rest, all the other interactions are part of the inelastic. So sometimes one of the questions that is often required, that we have been asked often is, what about quasi-elastic? Is part of elastic or inelastic? So first of all, what is quasi-elastic? Quasi-elastic is an interaction in which the projectile hadron interact elastically, not with the whole nucleus, because that is elastic, but with the single nucleons, with single neutron or proton, one or even more. In the final state, the target nucleus is excited. So this is part of the inelastic. So quasi-elastic is part of inelastic. And what is inelastic without quasi-elastic? Sometimes it's called production, because you really produce new particles, like typically pions, for instance. So the elastic cross-section is, of course, the total integrated cross-section for the elastic process. Similar for the inelastic is the total integrated cross-section, all the possible not elastic channels. And the total cross-section is, of course, is the sum of the two. But in Geom4, there are two different things, elastic and inelastic. And these two processes in a Monte Carlo transportation like Geom4, they are competing to each other, which means in Monte Carlo, we draw a random number, and according to the cross-section, we choose one of the other. Suppose that the inelastic cross-section is twice as big as the elastic, we throw a random number. If the number is below 0.33, we say this will be elastic. If it's above, then we say it's inelastic. So this is the way. This is true what I'm saying, that there are only two processes for hadrons, elastic and inelastic. It's true for all particles, pions, protons, alpha, deuterium, with only one exception, the neutrons. We will see where, for historical reason, there's nothing deep about that. For historical reason, the inelastic is further divided in radiative capture and fission. So there will be 4 just for neutron, but the principle is the same. You throw a random number and you choose which of these 4 processes according to the cross-sections. Yes, so regarding the inelastic final state, I said that there is competition between the elastic process and the inelastic one. Of course, there is competition at the same time also with non-hadronic processes, like ionization, for instance, for a charged particle, or decay, if it's a stable particle. And again, in a Monte Carlo, it means that we are drawing a random number and we choose which of these processes randomly according to the cross-section. And when, suppose that we have this competition at each step, and we select an inelastic process. What happens is that we use the cross-section for this competition between different processes. Once we know that the inelastic process wins, we don't use the cross-section anymore. We use the final state model to select which is the final state which is produced, okay? And one of the questions that we often hear is, suppose that you are interested to a particular final state in an interaction, 10 GeV proton or copper, you are interested to have K0 plus in the final state. So suppose that with your simulation, you get too many of these K plus or too few. So a typical question that we are asked is, where is in Geom4 the line where I can increase by a factor the channel which produce K plus in the final state? There is no such a channel. So there is no partial cross-section. So it's not that for each channel inside Geom4 we have the partial cross-section for each channel. There is only the overall integrated inelastic cross-section, which is for a given, let's say 10 GeV proton on copper is one number, and that's it. There's no other thing. And then we have a final state model which decide which is the final state. So if you want to change, to alter this kaon production, for instance, you need to go inside the final state model and change things, but there is not a single number. It's not an easy thing to do, okay? Okay, there is a special process which is called nuclear capture at rest. So first of all, at rest, it means that there is zero kinetic energy. Now, in the real life, it never happened that a particle is exactly at zero kinetic energy because there is always temperature above zero. We will never reach absolute zero. There's always some thermal motion. But of course, in a simulation, everything is simplified. So in Geom4, things goes really to zero, so that you have particles that, for instance, charge, they release, they ionize, they lose all their energy, they are exactly at rest. So when the things are at rest, there is not the concept of cross-section any longer. What matters is so-called lifetime. So what is happening for negatively charged hadrons like pi minus, K minus, antiproton, and so on, is that there is some lifetime when they are at rest that the surrounding nuclei somehow suck them in. And this is called nuclear capture at rest. And sometimes for unstable particle like pions, kaons, negatively pion, negatively kaons, this nuclear capture compete against the decay. So there again, we throw a random number and decide which of the two based on the lifetime of this process, no cross-section. There is no cross-section for at rest particle. Okay, so some physics model of cross-section needs some, are so-called data-driven. They need some numbers which are read in the initialization from some files. Or there are some heavy computation which is done offline, and then you read just the results just to be a bit faster. So automatically, for you, in many cases you don't even realize, Geom4 essentially relies on these files to read these things. And what is happening is that some environment variable shown here point to the proper files, and this with a version. So according to the Geom4 version, the version of these files can be different. So some of them, the one with light blue, are the ones that you get in nearly all physics lists. The one darker below is the one that you might use according to which kind of physics you will have. There is a description here on each of them. I will not go through because it's a bit boring, but the important thing for you is to know that behind the scene, GEM4 is looking for some files where some important information is contained regarding the physics. And here is the meaning if you are interested in. So neutrons. Neutrons are an interesting complication. First of all, it is abundantly produced, mostly at low energy, MeV, typically in the last phase, this nuclear de-excitation part, is the typical third most abundant particle after electrons and gamma in many applications. And of course, has around 50 minutes mean lifetime, so it can go around in your apparatus for a long time, for hours, but even if it stays a few minutes, it can have a large number of elastic scattering, and then it can either decay or have an inelastic interaction, for instance, and disappear in this way. And according to how precisely you want to model, in your simulation, what is happening to these neutrons when they are going around, the time of your simulation can change by an order of magnitude. Fortunately, for many applications, in particular the one of high energy physics, especially when they are looking for Higgs, for top supersymmetry and so on, the detailed, precise simulation of this neutron is not important. However, there are important applications which actually cares about this thing. And what is the most tricky part are the neutron below roughly MeV, because at that point, it depends really on the isotope where you have, and typically you need a data-driven approach. So GEM4 has such a more sophisticated treatment of neutrons. It's called HP for high precision treatment of neutron. It concerns neutron below 20 MeV kinetic energy down to thermal energy. Thermal energy means essentially below electron volt, essentially below 1 electron volt. As I said, they are neutron for historical reason are a bit an exception in GEM4 in the sense that they have 4 hadronic processes, not only elastic and inelastic, but they have also this radiative capture, fission, so elastic, radiative capture, fission, and all the remaining is inside, again, inelastic scattering. And this is one of the cases where there is a lot of data that is read in at initialization when you use this HP, and is pointed by this environment variable that in most cases you don't even need to know, but it is this G4 neutron HP data. And as I said, fortunately for most high energy applications, this is not needed to have this high precision. However, there are examples where, for instance, cavern background, shielding, radiation damage, radio protection, where it is very important. So how do you know whether HP is present or not? In most cases, it's easy. If you look at the name of physics list, if you see HP in the name, it means that there is this high precision model. If you don't see it, it is not there. There is an exception, of course, which is shielding. So you don't see HP appearing in the name shielding, but the name shielding should ring something, because it's one of the places where this neutron high precision treatment is very important. So in shielding, although you don't see from the name, this HP is used. A few words regarding hadronic showers, because this will bring us naturally then to the validation. So if you have a single hadron, think a 20 GeV pion, impinging on a large block of material in a high energy experiment is typical the calorimeter, where you have most of the mass of the thing. What is happening is that this impinging hadron will have an hadronic interaction at some point, which generates secondary hadrons, which are lower energy, which in turn they will fly. They will have, in their turn, hadronic interaction, which produce other secondary, and so on. You have what is called an hadronic showers. And these hadronic showers are quite tricky to simulate because they involve essentially all energy scales. Because even if you start at very high energy, even TV, you will get secondary lower energy, so you go down to thermal energy, so you have to use all the machinery of hadronic physics of Gen 4 in that sense. So that's why it's complicated and important to have a proper simulation of hadronic shower. Why it is important? Well, this is more for high energy physics. These hadrons, of course, are important for the simulation of jets. So jets are essentially narrow spray of a bunch of hadrons, and the simulation of a jet is the convolution of the simulation of hadronic shower for each of these constituent hadrons. Of course, for a simulation of jets is important also other things like Monte Carlo event generator and specific experiment-specific aspects like geometry, digitization, and pile-up, and so on. But it's extremely important to have a proper simulation of jets because they appear essentially in all the physics analysis here at CERN, either for signal or background. So this is an example where the simulation of jets and therefore of hadronic interaction is important for data analysis because you need to have a proper simulation of jets, but it's also important for the other usage of detector simulation, the level of detector design. And this is what is happening right now, for instance, for FCC and other future collider, where to have a proper simulation of jet is important in order to have a proper design of a detector that will cost a lot and will be built only once. So you have to build once with the proper properties. Now, physics list. We go quick because you have already heard before the concept of physics list, which is very important. That's why we return regularly. There will be one lecture on Friday dedicated in more details. So here I go very quickly. So what is a physics list? So it's a class where we specify all the particles, all the physics processes, and eventually also the production traction, which are needed by your Gen 4 application. So there must be one and only one physics list. There are no default. You have to make an effort to choose one, okay? And the reason is that it's a flexible way to build your simulation. So in principle, you could pick only the particles that you are interested in and only the physics process that you are interested in. However, you have to be careful because, of course, if you make a choice which is doesn't include important particle, you can get a simulation which doesn't describe the reality that you are interested in. So you have to be careful. The question that we hear several times is, in nature, of course, there is one physics, one set of particles, one physics. So why the hell Gen 4 make this complication for the user that they need to pick one of several physics lists? Give me the best that you can do, and that's it. And this is actually a choice that other Monte Carlo transportation code actually do. So they provide by default the best they can afford. We did a different choice because we think that it's not obvious at all that is the most precise thing that a Monte Carlo transportation can do, the default, the right choice. Because what you need in practice is not the best, most accurate one, but you need something which is accurate enough for what you need, but not more than that, and as fast as possible with that accuracy. And because there are several models, several levels of detail and accuracy in electromagnetic, but even more in hadronics, the idea would be that you need to think what you want, what is the degree, what you want to simulate, what is the degree of accuracy that you need. And based on that, you have to make a choice of what is best for your case. So, of course, asking each user to write from scratch a physics list with all the particles, all the interaction, electromagnetic, hadronic, it will take a long time, will be error prone. So what we do is we create a set of physics called a reference physics list, and we give some indication, some starting point where to start. But at the end, that's very important, is the user at the end of the day, which is responsible to validate that particular physics list. We give some suggestions, you will see later on, but then you have to make sure that is exactly the case for you. So there are several cases, and in most cases, the name describe the main physics, hadronic physics model. You see here. And sometimes if you see EM something, then is an option. For instance, EMZ here is the so-called fourth option, the most precise option that Gen 4 can offer for electromagnetic. The other are different combination of hadron models. For instance, FTF-BERT, this is our recommended physics list for high energy physics. So from the name, you see immediately the main component, FTF, which stands for Frithiof, which is an hadronic string model, which is used above 3 GeV. 3 GeV for pions, proton, neutron, for most of hadrons. Then we have the Bertini-like intranuclear cascade model, BERT, which is used below 6 GeV. So between 3 and 6 GeV, we have this transition where we draw a random number to choose between the two. The P stands for this nucleus de-excitation made of this two-step pre-compound and de-excitation or evaporation part. But then there are other things which are you don't see from the name, but it's important to note that they are. There is neutron capture. There is neutron capture of negatively charged hadron at rest. There is hadron elastic. There is gamma nuclear, electron nuclear, mu nuclear, standard electromagnetic physics. There is no neutron HP, so the treatment of neutrons is relatively simple. There is not the one of high precision. There's no radioactive decay. There are no optical photons. And these are kind of variants of that one. For instance, FTF-BERT HP is as FTF-BERT, but there is also this high precision treatment of neutrons below 20 MeV. Shielding, as I said, is an exception. So it's like FTF-BERT HP. Moreover, it has also a special model, which is called QMD, quantum molecular dynamic model, in the range between 100 MeV and 10 GeV per nucleon. Then there is FTFP INCL XX, so it's similar to FTF Bertini, but instead of using Bertini model, we are using a different intranuclear cascade, which is called INCL for some particle, in particular pion and protons and neutrons. Then there is this QGSP-BERT, which is similar to FTF-BERT, but we are using a different string model at high energy. There is this transition between 12 and 25, the one that I showed you before with a drawing. And then there is QGSP-BIC, which is similar to FTF-BERT, but is using QGS model and binary cascade. And this is the recommended one, for instance, for medical physics. Is the one which is used mostly for medical physics. Binary describe very well low energy protons. How to use a reference physics list? I'll go very quickly. As I said, there will be another lecture. You see, with one line, you include 5 in one line, you can specify the physics list. And once you choose a physics list, you have some room for customizing. For instance, you can take FTF-BERT and decide to use radioactive decay physics on top of it. You see, it's one line. There was a question before, how can I have? So this is how in one line you can enable on top of a physics list, which doesn't have radioactive decay as FTF-Bertini, you can enable radioactive decay, and similar for optical physics, for instance. Okay, so very quickly to validation. So first of all, why we need to care about validation? Well, for two reasons. First, of course, we are talking about the complex code with more than 1 million lines of C++ code. So there's plenty of room for mistakes and bugs from our side. And second, as I said, in hadronic physics, the models are quite approximate. So you really want to see how far you are from the data, essentially. There are two types of validation. One which is done by the developers, which is called thin target validation. Thin target, as the name suggests, is really a thin target, typically a few millimeters, where you have a well-defined impinging particle, and you look at the final state. So you know very well what is happening here. And this is what is used by the developer to validate. It's 40 minutes. Huh?
I understand.
But
if we can pause now, because you have another talk tomorrow. So you have another talk, whereas Makoto is in a different
Okay,
time.
okay.
So
I can continue next time. I can stop here, I think.
Sorry.
No problem.
So, sorry about that. I have maybe, let's bring in one quick question. And then we have other times when we can look at other questions. So the quick question while I bring up Makoto's, actually, while we deal with the slides, for TeV or hadron collisions, more specifically neutron-hadron collisions, what is this variable? Oh, there's this variable core interaction length, which is likely a mean-free path. After a neutron transits a single interaction within a medium, is the incident original neutron still there, or does it go away after making these strings?
So this path length, it depends on the cross-section. So for a given, when a neutron, as any other particle, has a given energy in a given material, we know the cross-section, elastic and inelastic in general. In the neutron, there will be 4 cross-section, elastic, inelastic, radioactive, capture, and fission. So the path length will be essentially related to this cross-section, basically. We draw a random number and we decide which of these things. So this will decide the length of the thing. After an hadronic, typically after an inelastic interaction, like any of these 4 apart the elastic, in general, you don't have a neutron in the final state. Or if you have it, is not related to the neutron that you have in the initial state. You have to think as only the elastic one somehow is the same, although in quantum mechanics you have to be careful, but is the same as the one in the initial state. For all the others, if you have a neutron in the final state, is a new neutron somehow. The original one, the projectile one, has been destroyed in some sense.
Okay. Sorry then, and thank you. So the final talk, the final topic is the definition of user interface commands. Makoto, thank you for your patience. We're projecting here. So give me a second to stop the recording and start a new one, excuse me.